Hello everyone, thanks for coming to my talk. Today I'll be presenting JSONML, a data-centric optimization framework for machine learning. This work was done at the Scalable Parallel Computing Laboratory at ETH Zurich and was done in collaboration with my co-authors listed on this slide. We'll start off by speaking about some general trends in machine learning. I'm sure many of you have seen some form of this figure before. This is plotting the training compute required to train milestone machine learning systems over the past decade. And the trend we see is clearly exponential. What's more is that several groundbreaking systems in fields such as natural language processing, reinforcement learning, and vision are often characterized by their ability to leverage large-scale compute effectively. The situation we're in is then one where researchers are demanding efficient large-scale computation more than ever. However, we also see that to achieve this efficient computation, almost all optimizations that are important in deep learning relate only to the data movement of the data within the accelerators. So this covers important optimizations such as operator fusion and hierarchical tiling. However, looking then at the current set of compilers, we also see that they're highly specialized. So they're specialized in terms of operators, transformations, and models. For operators, compilers often implement optimizations only for a specific set of popular operators. And this leads to situations where, for example, layer normalization was for years less performant than the more popular batch normalization, despite only being a change in the axis of computation. Then we find that transformations, even when they're completely data-centric, so these data-centric transformations such as operator fusion, in principle, don't depend on the computation that's being performed. However, in current compilers, we often find that just changing out one computation for another can completely destroy transformation passes and result in much worse performance. And finally, of course, these issues map to the larger landscape then, to models, and we find that actually deviating from the general set of popular model architectures can quickly lead to degraded performance because of this specialization. And as these frameworks specialize, they of course implicitly constrain novel approaches which drive progress in research. So once you run into such a distortion, you'll find that tuning or even just visualizing the output of one of these systems is incredibly difficult. What you get out of the black box is effectively what you have to deal with. And improving the characteristics usually entails large engineering efforts where you need to actually modify the system internally. To tackle these issues, we propose JSONML. JSONML is a data-centric framework for multi-level lowering and optimization of machine learning workloads. It has three main goals. Firstly, we'd like to keep the usability of the powerful model definitions that researchers are used to and translate this to optimization. Next, we'd like to stray away from the operator-centric mentality in optimization and use general-purpose data movement reducing transformations that generalize, hopefully not only across the operators today, but also across operators in the future. And finally, JSONML has very powerful interactivity features that allow you to unpack the compiler black box and tune and understand your workloads the way you like. So how do you actually use it then? Here's an example PyTorch module. For those that are not aware, this is a rather simple one. This is just a linear layer here, so this is effectively a matrix multiplication. And then here in the forward pass of the model, we can see that this linear layer is being applied, and then the output is being divided element-wise by this parameter here. To bring this into the JSONML framework, you only have to change one line, which is this DACE module decorator on the top of the module. With this one line change, you can now bring the model into the JSONML framework and do all the powerful optimization that we'll talk about in the rest of this talk. So then here's the overview of the system. At the top, on the front end, we have the PyTorch decorator we just described, as well as for other frameworks, we use the ONNX exporters. So we leverage the ONNX representation to import these models. And in this ONNX representation, we also do a symbolic shape inference pass to annotate every intermediate shape, every intermediate value with its symbolic shape. Then, once we've done this, we can really easily bring this model into the data-centric intermediate representation. And here we do our different passes, such as automatic differentiation, lowering and specialization, and finally code generation. And this is a progressive lowering pipeline, and along which we do multi-level optimizing transformations at each step of the way. Finally, we generate high-performance code for CPUs, GPUs, and FPGAs. So now let's talk about the representation. So this is the stateful data flow multigraph representation, or SDFG for short. And this is a representation where data movement is central and always explicit. So here we can see one state of the representation. So this is what we call an STFG state. And this is just essentially a data flow graph. So as you can see, we have data nodes, we have compute nodes. And yeah, to actually perform a computation, you first need to access the data. And so this is done using these access nodes here, rather simple. And then these arrows are what we call memlets. So these denote explicit data movement, and this is done at all granularities. So this can be either transferring a whole array or even just a single scalar. And notably, the data movement information of these memlets is propagated so that every single scalar access across the whole program can be traced at all in constant time at all points in the optimization pipeline. So then, to actually perform a computation, here's a simple example of a tasklet. A tasklet is just a stateless computation that's opaque. And in the nature of data-centric transformations, we don't actually care much about these the internals of the tasklet. So for almost all the transformations will not look at this at all. And yeah, to actually then perform this division here, as you can see, we need to move firstly the inputs into the tasklet. So this is done here. And then we need to write the output out to an output buffer. Now, to do parallelism, we have these parametric parallelism scopes, which we call maps. And these are just kind of like parallel for loops. So this internal subgraph here is repeated as many times as denoted by these iteration variables. And then these iteration variables are used on the memlets to actually read different regions of the input data every time for every iteration. And then finally, this operator node up here. This is a matrix multiply. We call this a library node. So this is just a node with domain-specific semantics. In our case, these are ONNX operators. So there's a gem ONNX operator. There's around 150 ONNX operators. And these library nodes can then be lowered to one of several implementations. So by default in JSONML, we have opaque ONNX runtime implementations for every kernel. And these are usually good enough to get high performance. But then to actually do our transformations, our data-centric transformations, we need to lower these to data-centric representation. And this is what we call a pure implementation. So where we lower like this library node to another stateful data flow multigraph. So now let's look at the pipeline. So this is the full pipeline here. We talked about the input stage over here. Now let's talk about the multi-level optimization. So the first stage is coarse grain transformation. And this is, at this point, the ONNX nodes were just brought into the representation. So as you can see here. And we already do some intermediate lowering. So for example, here, this is a section of a BERT, a transformer layer. And you can see that this einsum over here was originally a transpose. So that's already been lowered by one step. And in this representation, we can do these transformations like algebraic fusion, where this transpose is fused into the subsequent batched matrix multiplication. And we can also do things like constant folding. So this whole shape computation, these types of shape computation trees are very common in ONNX exports. And yeah, ideally, you just want to clean all of those up. Then now let's talk about lowering to a pure implementation. So to do this, in other frameworks, you usually have to write a kernel implementation for each type of operator. The approach we take is where we leverage the Python parsing frontend from the DACE framework. So this allows us to actually write these kernel implementations as very simple NumPy programs. And these are, of course, familiar to the practitioners in the field. So here you can see that this soft plus operator was just implemented as a sequence of element-wise operations in NumPy. And note that there's no notion of optimization here at all. So this is just the pure naive implementation. And this will then be transformed using the same generic data movement reducing transformations that are used for all operators. And in particular, actually naively lowering this will actually result in 3 subsequent kernel launches. So this is very naive. So now let's look at this data movement reduction. And this is the local data movement reduction stage. And for this, we'll be using this example up here on the left. The details are not important. This is just a MISH activation. So it's a soft plus, a tanh, and a mul. So just a sequence of element-wise kernels. Now, naively lowering this, as we said, we'll just produce this sequence of element-wise kernels. And of course, this is quite suboptimal in terms of data movement. So here, we're reading and writing from global memory in between each of these kernel launches. So here, this is full read from global memory, then a full write to global memory, and then repeated a bunch of times. To reduce the data movement here, of course, the natural thing to do is to do loop fusion. So we call this map fusion. And here we've done map fusion and actually as well some vectorization on the last dimension to produce this fused kernel. And of course, here the data movement is optimal. So we're just reading from global memory once and then writing out the result once. And notice, because this is a data-centric representation, we don't actually care about the computation that's being performed here internally. We just care about the data movement patterns. And as soon as those patterns match, we can apply this transformation. So now let's talk about supporting training. For that, of course, we need to compute gradients. And in JSONML, we choose a slightly different approach to the other frameworks out there. So first of all, of course, we need some model data for this, model metadata. So this comes from just PyTorch from the annotation. And we just automatically use that metadata to determine what gradients we need to compute and so on. So then in a typical framework, the way you actually do automatic differentiation is you go backwards in the graph. So you traverse the graph in reverse topological order. And for each operator in the forward pass, you insert a manually handwritten backward pass kernel. So in this case, here we've introduced a backward pass for the ReLU operator. Now note that this is a full kernel that needs to be written. So there's mathematical derivation rules, of course, that need to be applied to determine what needs to be computed. And then you actually also need to write the kernel in a high-performance way to perform the computation. And then you do this for every operator. So every operator needs a backward kernel, and you do this across the whole graph. So that's how that works. Now in JSONML, of course, in our representation, we have a lot more information available to us. And so the approach we actually choose is a novel approach of symbolic automatic differentiation. So this reformulates automatic differentiation as a data-centric transformation. And in effect, this is a source transformation approach to automatic differentiation. So we'll look at it in this example here. This is just an element-wise log. And note that the input, which we're going to be differentiating, is not actually an opaque operator like ReLU here. This is actually already lowered. So this is lowered to a loop, so a parallel loop, and this tasklet, which performs the computation on every scalar in the graph. So then to do AD, all we do is we go through this graph in a similar way and do the insert backward nodes for each of the nodes. But notably, the nodes that we're reversing are not actually operator nodes, but rather the nodes of our lower level representation. So here we've reversed the access node, which produces this gradient access node. Then we reverse the maps. And then finally, this is where it gets a bit interesting with tasklets. To reverse a tasklet, actually, in general, of course, reversing like a full operator requires you to manually specify the rules to produce the backward pass. But since this is actually a scalar expression, we can just use off-the-shelf automatic differentiation tools, such as the SymPy AD engine. And this produces a scalar expression for the gradient. So that's what was pasted in here. And then the engine leverages all the data movement information, which is implicit in our representation, to properly connect this all up. So here you can see it's introduced this connection for this value, which is forwarded from the forward pass. So sometimes this is required in automatic differentiation. And then it's also noticed that this read may conflict, so it's introduced a write conflict resolution to sum up the gradients across the reads. So in essence, we can automatically synthesize backward passes for every kernel in the framework. So every kernel that is defined using this Python front end, which we showed earlier, we can automatically differentiate. And this means that the vast majority of the kernels in the JSONML framework are actually differentiated automatically, and we don't actually have explicit backward passes for them. Now, this actually enables a new class of optimizations which are not available in other frameworks. And those are the optimizations that are done before automatic differentiation. Because note that, like I said, this kernel that we're differentiating is actually already lowered. So since we can differentiate lowered kernels, we can actually perform optimizations and then differentiate that lowered kernel. And this will produce different results than swapping the order, so than doing automatic differentiation first. And we can see that in this case here. So this is the same MISH operator. If we do automatic differentiation first, we get all these global reads and writes for these intermediate values, which needs to be stashed and forwarded to the backward pass. So here we're reading these values from the forward pass, and this is of course a lot of data movement, which is not good. In DACE, we can, by differentiating, by first doing the fusion, then differentiating the fused kernel, we get this backward pass here. So this is the backward pass that is generally like that. And we can see that in terms of intermediate memory and in terms of data movement, this is actually optimal. So here, this uses on the order of hundreds of megabytes of intermediate memory, and here we're using none at all. And we'll see later on in the evaluation that other frameworks actually fail to perform this optimization because no other framework can actually do automatic differentiation on a lowered representation. They all do this operator level AD, which has impacts on performance as well. So now let's talk about global data layout optimization. So in the SDFG representation, the memlets and the code generator are completely data layout aware. So we can just tweak the data layout of any value here in this graph, and the code generator will just transparently support that. This is really powerful. So we can use this to globally, to modify, for example, the data layouts of a transient here in the middle to be globally optimal. And in particular, we can also prune layouts that don't permit a specific lowering. For example, here we can prune layouts from the search that don't permit lowering this einsum to a blast call, which is something we'd usually like to do. So finally, let's talk about hardware specialization. Of course, this is incredibly important in deep learning. And for this, we'll use the common example of softmax. So here is, once again, the operator implementation for softmax is written completely in NumPy. This is exactly what how it would look if a NumPy user wrote a softmax operator. And then the naive lowering here just produces the sequence of element-wise kernels. So here, this is a reduction library node that corresponds to this maximum computation. Then here, the exponent with the broadcasted subtraction. Here, the sum reduction, and then finally the normalization division. So after, of course, then in the local data movement reduction stage, this would all be fused into one kernel. But to then efficiently lower that to hardware, we need to do a new transformation. And this is one example of a hardware specializing transformation. We call this warp tiling. So for GPUs, this transformation will tile the computation in the last dimension along the warps of the GPU. And this is once again a data-centric transformation. It doesn't care about what's being computed. It just cares about the patterns of data movement present in the operator. And in this case, the transformation will do things like replicating computation and lowering to specific hardware-specific reduction implementations. So here, for example, this max reduction has been lowered into 3 separate tasklets. And these tasklets correspond to warp reduction implementation, which removes the synchronization overhead, which is not required in warps. Then here we can see that this exponent was replicated, and this permits fusion. And this is of course necessary for this lowering. And then here another warp reduction for the sum. And then finally this division was also fully fused with the preceding exponent computation. So here is an example where data-centric transformations are actually being used to do hardware-specific lowering. And we'll take a look at the performance of this in a sec. So the last step, as we said in JSONML, is that we have a white box approach to optimization. So in particular, you can introspect all parts of the pipeline. You can do this using visual tools, and you can also do this using codes. You can insert your you can tweak and insert your transformations at every step of the way. And one of the more powerful features is this VS Code extension. This comes from the DACE framework as well. And this allows you to not only interactively view the graph, but also change almost all aspects of the graph. So you can apply transformations here on the left. You can see all the applicable transformations. You can change data layouts. You can insert nodes and so on. And we actually have an optimization case study for EfficientNet where we perform the full optimization only using this Visual Studio Code extension. This also, of course, has powerful visualization capabilities. So here, since we know everything about data movement, we can easily overlay memory volume, so the amount of data transfers that are required, and also static flop analysis for computation. So there we go. That was the full pipeline. We went through the front end with the Onyx nodes, coarse-grained transformations here on the Onyx level. Then local data movement reduction, mainly through different types of fusion. Then our new approach to symbolic automatic differentiation that allows us to skip writing backward pass kernels and then also do this new class of optimizations where you do optimizations before automatic differentiation. Then we looked at our capabilities in tweaking global data layouts. And finally, hardware specialization, where we specialize the code to the particular platform. So now let's take a look at some results. So here is this MISH operator that we mentioned a lot when we explained the lowering pipeline. And this is actually the case where the pre-AD fusion achieves the minimum in data movement that we mentioned. So of the other frameworks, only one, actually XLA in the TensorFlow case, manages to produce a single fused kernel. And even XLA, which is one of the state-of-the-art training compilers, failed to eliminate the global loads and stores that were introduced to stash the intermediate values. So then of course, here we can see that since JSONML achieves the minimum in data movement, we achieve the state-of-the-art performance for this operator. Then we have softmax here. So this is the other operator we saw in the hardware specialization stage. And we can see that JSONML, the generic data movement transformation, managed to match the handwritten kernels from other frameworks such as Triton or PyTorch, and actually generalizes transparently to other operators because it doesn't actually depend on the computation being performed. Now, here are the results for the full models. So we can see here that we're testing across a range of models, from vision to non-convolutional vision to transformers, audio models, and recommendation systems. And we can see that even this is using only our automatic optimization pipeline. So this is just the data movement reducing pipeline without any user guidance. Even just with that pipeline, we manage to sometimes outperform all the other frameworks, and we almost always match them. So we kind of see in JSONML this as the base level of optimizations that is done automatically for you. And then, of course, the key capability of JSONML is the ability to then go further. And we explored this in 2 guided case studies on heavily contested networks. So the first is EfficientNet. This is the case study where we completely do all optimization using the Visual Studio Code extension. And we can see here annotated that you can get these transformations to apply in just very few clicks. And in particular, we find a new fusion opportunity, which is not leveraged by any other compilers. So this is exposed only after swapping the iteration order of a reduction. So now let's look at the results of these case studies. So for BERT, where we take the more code-based approach, so there we hook in using the Python API and modify the lowering pipeline like that. And there, the guided optimization actually achieves state-of-the-art, so on both the forward and the backward pass. So this is outperforming all the other frameworks. And the same happens on EfficientNet. So here, this was, like I said, the case study with the Visual Studio Code extension. And here, even just with a few clicks, you can outperform all the other frameworks in a very easy-to-use way. So that concludes the presentation. So to summarize, we introduced our data-centric approach to an intermediate representation for deep learning. We talked about how we lower this intermediate representation to efficient hardware codes. And we spoke about results, not only for single operators, where we found that our generic data movement reducing transformations managed to match the performance of handwritten kernels of other frameworks, but also on full models, we found that using our guided optimization strategies, are able to match these highly contested and highly important networks like EfficientNet and BERT and achieve state-of-the-art performance there. So thank you very much for attending the talk. All of our code is available on GitHub under this URL, and we hope that you get some time to play around with it, and we're, of course, always happy for feedback.